Welcome to the Explainer. Today we are jumping into one of the biggest leaps you'll make as a structural analyst, that move from linear to nonlinear thinking. If you've ever run a simulation and just had that gut feeling that the simple, clean results weren't quite telling you the whole story, well, you are definitely in the right place. Look, in the world of finite element analysis, we all cut our teeth on linear analysis. And why not? It's built on this really elegant, simple idea. The relationship between the force you put in and the displacement you get out is just a straight line. The structure's stiffness is considered constant, so we can solve the whole thing with one clean equation. It's super fast, it's efficient, but it's also a perfect world scenario. But here's the catch, right? The real world is, well, it's messy. Materials yield, big parts bend a lot, and things bump into each other. The second any of that happens, our nice, neat linear assumptions start to fall apart. And if we're not paying attention, they can lead to results that are dangerously misleading. So the million-dollar question is, how do we know when it's time to step out of that comfortable linear world? So here's our game plan. We're going to map out this whole territory, starting with the absolute limits of the linear world. Then we're going to meet the three big sources of nonlinearity. We'll dive into each one with some real-world examples, and finally, we'll pull back the curtain and see how modern solvers actually figure out these complex problems out. Okay, first things first. Before we can break the rules, we have to know what they are. To really get when to go nonlinear, we've got to be absolutely crystal clear on the assumptions that make linear FEA work in the first place, the very things that make it so fast and simple. So linear analysis really stands on three main pillars. First, it assumes that any deformations are tiny, so small that the basic shape and stiffness of the structure don't really change. Second, it assumes materials are perfect little followers of Hooke's law. They stretch, they spring right back, no permanent damage. And third, it assumes that all your connections, all your loads, all your supports, they stay put and don't change throughout the entire analysis. And that right there is the whole ballgame. The second, the instant, any one of those assumptions gets broken in the real world, our linear analysis starts to drift away from reality. And this is the scary part. The numbers can look plausible, the colorful plots might look totally convincing, but they could be telling you a story that is just plain wrong. Okay, so where does all this real-world complexity come from? Well, it's not just random chaos. It turns out that basically every single case of structural nonlinearity can be traced back to one of three specific physical sources. If you can understand these three, you got the key to the kingdom. And here they are, the big three: geometric, material, and contact, which you'll also hear called boundary nonlinearity. Now, sometimes a problem is driven by just one of these, but more often than not, you've got a couple of them, or even all three, happening at the same time, interacting in really complex ways. I love this table because it's such a great roadmap. Just look at how each type has a totally different source. Geometric is all about the shape changing. Material is about the properties of the stuff itself. And contact, that's about how different parts interact with each other. And you'll notice each one messes with the system's stiffness in a unique way, which is exactly why the solver has to work so much harder to find an answer. All right, let's talk about number one, geometric nonlinearity. This is what happens when a part deforms so much that its own new shape completely changes the problem. Think about it. The stiffness isn't a constant anymore because the geometry itself is basically a moving target. What this really means is that we can't get away with solving our equations on the original, perfect geometry anymore. Nope. The solver has to constantly update and calculate the forces on the new, deformed shape. This is a huge distinction, and it's something a linear analysis is completely blind to. So when should the alarm bells for geometric nonlinearity start ringing in your head? Anytime you're dealing with something long and skinny or thin and flexible. We're talking about a fishing rod bending way over, a cable on a bridge swaying in the wind, or that thin metal column that's about to buckle. These are all poster children for cases where the changing shape is the main character of the story. The classic P-delta effect shows this perfectly. So imagine a tall column. It's got a big weight, P, pushing down on it from the top, and a little sideways force, V, pushing it from the side. Now, in a simple linear analysis, the bending moment at the bottom is just that side force, V, times the column's length, L. Simple, right? But in the real world, that side load makes the column bend over by a little bit. Let's call that distance delta. Well, now that huge vertical load, P, isn't perfectly centered anymore. It's offset by delta, and that creates a whole new, additional bending moment. And here's the kicker. That extra moment causes more bending, which increases delta, which in turn increases the moment even more. It's a feedback loop that linear analysis completely, totally misses. Okay, next up, we're diving into two sources of nonlinearity that are all about raw physical reality. What happens when our materials stop behaving perfectly? And what happens when different parts actually touch, slide, and maybe even separate? Material nonlinearity is basically what happens when you push a material past its elastic limit. You know, that point of no return on the stress-strain curve. We are way off the straight-line path of Hooke's law now. Once a material yields, it's changed forever. It deforms permanently, and its stiffness is never the same. This covers all sorts of things. It's the permanent bending you see in a metal car frame after a crash. That's plasticity. It's also that unique, super stretchy behavior of a rubber seal or an O-ring. That's called hyperelasticity. It can even include things that happen over time, like creep, where a plastic dashboard slowly starts to sag under its own weight on hot summer days. And last but not least, we have contact. Now, of the three, this one is often the most difficult to get a solution for. And why is that? Because it's fundamentally an on or off problem. One moment, two parts have a gap between them. The next moment, bam, they're touching. That isn't a smooth, gradual change. It's an abrupt event that causes a sudden, massive shift in the stiffness of the entire system. Just think about all the complex stuff happening inside a bolted joint, with the preload, clamping down, and friction holding things in place. Or picture a plastic snap fit feature clicking into its final position, or even just two simple blocks being pressed together. Every single one of these events, gaps closing, surfaces sliding, parts separating, the solver has to detect it and figure out what to do next. So, it's one thing to know about all these challenges, but how in the world do modern solvers actually navigate this incredibly complex, constantly changing landscape to find an answer? Well, it's not a single calculation, it's more like a journey. Instead of trying to solve the whole problem in one giant leap, the solver is much smarter. It applies the load in tiny little pieces or increments. And at each one of those tiny steps, it does a series of iterations, kind of like a very educated guess and check, to find the new point of equilibrium where all the forces are perfectly balanced. It's literally like it's carefully walking its way along a winding solution path one step at a time. Of course, sometimes the solver gets lost on that path, and you get that dreaded failed to converge error. Now, when that happens, it is almost never a bug in the software. It's usually a sign that something's up with your model. So here's a professional's checklist. First, check your constraints. Is your model properly held down, or is it just floating in space? Second, try applying the load more slowly with smaller steps. And third, take a very, very close look at your contact settings. And this gets us to one of the most important lessons any analyst learns. A convergence failure isn't a bug, it's a feature. It is your model shouting at you that the physics you've set up are unstable or just plain unrealistic. Maybe a part is about to buckle violently, or it's trying to fly off into space because you forgot to define contact. That error message isn't a failure. It's a clue pointing you to a deeper physical problem. And all this really brings us to a final thought. Learning to master nonlinear analysis isn't just about chasing a slightly more accurate number. It's about a complete shift in your engineering mindset. It's the difference between just slapping on a factor of safety and calling it a day, and instead pursuing a true, deep understanding of how your design is really going to behave, how it's going to fail, and how it will succeed in the messy, complex, real world.